Good afternoon, everyone. The first speaker is Wan. Today, the topic she wants to share is establishment of environmental level photon equivalent dose measurement technique. Let's welcome.
And hello everyone. Today I'm going to talk about the establishment of environmental level photoequivalent dose measurement technique. And this is especially for cobalt 60. And I will talk about the background, equipment, methods, and conclusions. And first of all, we talk about the background. And the reason why we should establish this system is because nowadays people are very concerned about some nuclear radiation, radiation pollution, food or radiation safety. And some green groups will take some measurement, like they will take this in measurement instrument to detect the environmental level of the dose of level. So we are in our lab we lack of accurate calibration standards, and because our lab people, you know that we're working at the NRSL, and we have some limited calibration capability because we only can calibrate up to about 10 microsieverts per hour. So it's almost about 50 for our about our background radiation. So we have to know that what is the measurement discrepancy between some instruments. So in order to reduce the consistency and reliability of the measurement results, so we should establish this system. So we use a cobalt 60 to simulate some high energy radiation ranges. And so before we start our topic, we should know that compared to other countries, what is our system? And you can see that this is some environmental level laboratories in various countries. And as you can see that in England and in China and Korea and some international countries, we can see that from Nigeria is Japan, they can detect about almost 20 nanosievert per hour. And for NIM from China, they can detect almost zero point 0.1 nanosievert per hour. And for PTB from Germany, we can detect almost 2 nanosievert per hour. So what is about us? And so let's begin with some my equipment. And this is my equipment that it is a 10 liter severe graphite ionization chamber we use in this system. And for this ionization chamber, we can see that it is very large compared to the common ionization chamber. It is in order to reduce the leakage current. And this is our in-house developed pressure regulator. And we use this gas bottle and this pressure regulator to regulate the gas into our ionization chamber. And I will introduce that. And for this, we will use the electrometer and some electromagnetic shooting box. And this is our environmental level shooting device. And this is our radiation source ionization systems. And first of all, it is our radiation source irradiation system. So we have three kind of sources: cobalt 16, cesium 137, and americium 241. And for cobalt 16, we have its own source road. We made it, and for cesium 137 is also, and americium 241 is also. And what is about our method? And to assessment of cobalt 16 beam film and its uniformity, we use the AT1121. It's a radiation detection instrument like this. and we put the A4 paper along the axis and y-axis, and we change the A4 paper thickness to show the different distance from the sphere center. And we can see that in this diagram. This is 0 point, about the 0 point here, and we use plus and minus 5 centimeters along, and to use this 8121 instrument, and to do the loss distribution evaluation. And you can see that it is almost here is 20 centimeters here, and this is also, so we can know that the field size is set about 40 centimeters, multiplied 40 centimeters. And next, how can we shoot the radiation? And we use this radiation shooting box, and it is made of lead. And this is the very special shape. It's called ellipse shape. And we can know that this is some ruler here, and we will use different distance to make this shoot and move back from 60 to 120 centimeters. And we can see that we can, in order to reduce all the system's radiation, and so we will have this shooting box here. And you can see that in this diagram, it is our position about 3 different kinds of position, and can see that if it is far away from our system, it has a big greater radiation intensity here. And because we said that we use a large volume ionization chamber, we will use to fill some nitrogen inside in order to reduce the leakage current. So nitrogen, we will use this nitrogen gas bottle, and this is our handmade barometer pressure regulator. And this is our barometer, and we can use it to know how is the condition into our ionization chamber. And this is our flow meter. And this is the diagram that shows that if we don't use this assistance system, we will have some leakage like this. And if we use it, this has better condition here. And in order to simulate the spectrum, we use a FIT system, FIT program, and to simulate the radiation source of environmental system. And FIT is called Particle and Heavy Ion Transfer Code System, and it is used as the Monte Carlo particle transfer simulation program. And we will use this because some FIT program is used to auxiliary technology or radiation therapy or some space radiation and particle transfer phenomena simulations. And this is our result of it. The program will be used to, we use the cobalt-60 as a point source to simulate this spectrum. And we can see that it is a cobalt-60 energy, and this is our FIT code. And we can see that it's as a point source. We can see the 1.117 and 1.33 mega electron volts here. And this is our spectrum shown. And for establishment of cobalt-60 source and antennator geometry, we use FIT as it. And we can see that it is our antennator energy painting here, and it is our source rod here. And we can know that radiation source irradiator and in the radiation rod energy painting we use here, and we can have its simulation like this one. And this is our particle check. And you can see that this is the irradiation rod here, and it is the air here. And because we have different kinds of attenuators here, so we have to simulate what is the particle check here. and we can see that this is our irradiation system here, and this is our 10-liter ionization chamber here, and this is our particle track here. And as different kinds of antinators, we have different kinds of particle track here. And for this one, we should know that this is the code of irradiation source. And this is because the cobalt 16 is a photon source, and we can see the primary photon energy here, and what is the code of the attenuators. And this is our primary, the cobalt 16 simulated energy spectrum here for our system. So that is the simulation. So we have to do what is the practical measurement here, and we use a portable HPGE to do the measurement. And we just like this, we can get the energy and count, and we have about the non-attenuators and with the attenuators here, and we can get the energy of cobalt 16 spectrum. And because we have to complete the ionization chamber area Kerma rate here, and in order to transfer to our laboratory, so we have to put it into our primary standard laboratory. And in our cobalt 16 primary standard laboratory, we use about 99 cc spherical rapid ionization chamber like this, and this is smaller than our ionization chamber. And we use this primary standard dose rate of the radiation field, and we calculate it with this formula. And all this calibration factor here is to calculate the radiation field of the standard dose rate, and this is our standard dose rate. And because this is smaller than our ionization chamber, so if we want to calculate our ionization chamber, we have to put it about SID about 4 meters long. So it is a little bit difficult. So we use after we calculate the primary standard, we use this system, and we move this system into the primary standard laboratory here. And we use our ionization chamber here as the secondary standard. And because we measure at about -600 volts, so in our system, so we also use this in our system. So to use this, we can know that we also have to gas field system to move here, and the barometer and electrometer and the high voltage generator here. And we can use the calibration figure for this one, because we can know that in our system we have the exposure current to measure in our system. And later we use the calibration system, the primary standard. There we calculated it and modify it, and we can know that the calibration figure here. And so we can know that the average converted charge of phantom from this is this account, and later we can know that what is the Kerma rate for it. And about my conclusions. Later we have to complete the equivalent dose calculation and the measurement uncertainty evaluation. So according to the ISO document, we can note that because we calculate the current there, so we have to change it into the equivalent dose. And the Kerma there and the Kerma to equivalent dose conversion figure is about 1.16. And we will use the standard Kerma rate of this radiation we measured before and convert it into the ambient dose equivalent. So this is our own final result for about 2 microsievert per hour. And we should use the uncertainty below into our environment. And so all the overall the uncertainty of the composite standard radiation field system was determined to about 2.58%, and for K over 1. So this is all my reference, and this is all my topic. Thank you.
Have any question? We have a question. Yeah, page 5. Yes, this is 5. 5. Yes. And why means they is capable of detecting such low value.
Means can detect about 0.1.
Yes.
Because in China they construct the laboratories underground. They construct a tuner underground, so they can shoot all the cosmic radiation and some radiation in the environment. So maybe they can detect much lower level of those rays.
I want to ask PhD. PhD is here mentioned the distance is around 60 to 120 centimeters. And how did you choose the distance?
We choose it just randomly. We just randomly choose the just far away from our shooting box because it's limited distance here, so we can't choose far away from this. So just inside all this one. So maybe we just choose random. Okay.
Would you go back to the nitrogen system? So you say that if the gas is nitrogen, it can reduce the leakage current. So why there's a leakage of the current? The reason
So why?
from the system why there's the leakage current.
There are many reasons about this. Maybe just some radioactive nucleus inside the air. So we just assume that there is some radiation inside the air. So in order to reduce the dose rate of our system, so we have to fill some nitrogen here.
So have you ever test other kind of gas?
No. Because in our lab we always use nitrogen. But I think maybe it is because it is 惰性气体, so maybe it's much can maintain well performance. It's more stable.
The second thing I want to ask, how do we check to fill such a so large ion chamber with nitrogen gas?
How long? In this picture, we can see that we use 10 SCCM, and it is the units that for STP and standard temperature and pressure, and we use 10, so almost for 1,000 10-liter ionization chamber, we will charge about build up with the gas about almost 60 hours.
60 hours.
16 hours, almost a night. So we will use it from the morning. We will place it to measure it, and later tomorrow we will take the result of it.
If there's no question, thank you.
Next speaker is Wei Han Shu, and his topic is standardized TC99 and radiopharmaceutical activity measured using a self-developed 4-pi X gamma coincidence counting system. And let's welcome.
Good afternoon, everyone. My name is Wei Han Shu. The topic I want to share with you is the standardized TC99 radiopharmaceutical activity measurement using a self-developed 4-pi X gamma coincidence counting system. And this paper will be presented at ICRM this year. And here are outlines for your reference. Let's talk about the history of the development of TC99. And we can see in 1977, TC99 is discovered, and in 1960s, TC99 introduced for medical tracer use. And in BNL here, BNL developed the first generator system for on-site production of TC99M, and the scientist Margaret played a significant role in the development of the TC99 generator. So TC99M is the most common used medical isotope in the world, and its birthplace is BNL. And the overview of the TC99 usage. TC99 is the cornerstone of nuclear medicine, widely utilized in approximately 80% of diagnostic nuclear medicine procedures worldwide. And TC99 is particularly suited for image techniques such as SPECT and scintigraphy. And it has a short half-life and more energetic gamma emission. Numerous FDA-approved TC99M radiopharmaceutical compounds are available, such as NDP and DTPA. And next is establish a national transport standard. Accurate radioactivity measurement is essential in our lab. NRSL was born with the responsibility of establishing and maintaining the nation's measurement standard on the area of ionizing radiation. So in this study, we want to establish a national traceable standard for TC99M activity in Taiwan. And next, I would like to briefly introduce how the primary standard for TC99M measurement was established in Taiwan. Our laboratory developed a primary standard using 4-pi ES gamma coincidence method. To confirm its reliability and constancy, we use a Siemens LSC method to validate. After establishing the primary standard, the standard was transferred to 4-pi gamma or the dose calibrator, and this is the second standard system. This allows for determination for calibration figure by combining the primary standard result and the ion chamber calibration result. We can get the calibration figure. Common radionuclides that domain scale. Many hospitals maybe transfer the stores into our lab, such as TC99M or Gallium-16. And there is a material method. According to the decay scheme of TC99M, it emits several radiation types, such as gamma ray, electrons, and X-rays. So, according to the decay scheme of TC99M, we use the 4-pi ES gamma coincident counting method that simultaneously detects beta particle and gamma rays. So measurement data include the gamma ray 140 keV gamma ray, and the electron and the gamma rays and the coincidence event. Here I illustrate the 4-pi beta gamma coincidence method. It's an absolute primary method for activity measurement. Here is an example for simple two-stage beta gamma decay. This method is governed by these three relations. MV is beta counting ray, N gamma is gamma counting ray, and NC is coincidence counting ray. So this system includes beta channel, gamma channel, and coincidence circuit. By using this, we can determine the absolute activity M sub O, and we can calculate the result. Here is M beta and N gamma over NC. Next. When dealing with the radionuclide that have multiple beta branch, the efficiency equation become more complex. However, we can rearrange this relation into a linear form as shown here. And next, we can draw a plot. Maybe we can plot the parameter N gamma over NC minus 1 on the x-axis. And the N beta and gamma over NC on the y-axis here. So we can get a linear plot. We try to change the detection efficiency typically by modifying the self-absorption radio source. The data points show a linear relation which was extrapolated to the intercepts corresponding to an efficiency of 100%. So this point we can get the absolute radioactivity. Now, let's briefly introduce the detectors used in this counting system. Our system consists of two primary components. One is a proportional counter, and this is the picture, and the other one is sodium iodide detector. So we can see the system is here. This one is the 4-pi proportional counter, and it is filled with piton gas. And the type of the word of the proportional counter is the sodium iodide detector. It detects gamma rays. And this is the simplified Bragg diagram of counting system. This is the gamma detection side, and this is the beta detection side. Finally, after being synchronized through deck time and resolving time control, both gamma and beta signal feed into the coincidence unit. Just like introduced previously, we do deck time correction. Most 4-pi ES gamma coincidence counting systems, including ours, use the non-extensible deck time correction. And here is the correction. And the next, we also do the resolving time correction. And next, let's talk about what is Siemens method. It has 6 steps. One is measure the standard sample here. We measure a standard treating sample under various quenching conditions to determine its detection efficiency against measurable quenching parameter. And 2 is theoretical efficiency for treating under ideal conditions are calculated, establish relationship, and we can get the efficiency and the free parameter relation. And the third, by combining its experimental result with the theoretical calculation, we can get the quenching curve. And the fourth, use the theoretical calculation, we establish an efficiency relationship for the unknown sample with respect to the free parameter. And the fifth is the unknown sample's efficiency is then found by applying its major quenching parameter to quenching curve. And finally, we can calculate the sample's activity. For the primary standard for TC910 validated using CN method, just as I previously introduced, and evaluated by weighted mean to determine its specific activity. And this is the equation for your reference. To make proper counting rates for different counting methods, the TC99 solution was diluted. Additionally, various source preparations were made, such as Lean source is for 4-pi ES gamma method, and the ample source is for 4-pi chamber and the dose calibrator, and the LS source is for CN LSC method. For 4-pi ES gamma coincidence method, the model solution underwent a 2-step dilution process before source preparation. The second stage used the dilute solution as a source for beans. Here, for beans, and the ample source is for 4-pi gamma chamber and the dose calibrator. And for CM method, the model solution underwent a 3-step dilution process before source preparation, and the LS source is for LSC counting, and the ample source is for ion chamber and the dose calibrator. The dilution factor is here for your reference. And the backing of the radioactive sources used to measure charged particles must be homogeneous, chemically and mechanically stable, and electric conductive. So common application use gold-coated beans foil. And this is the bean source preparation. First, we prepare bean solution. Then we use the water-based method to coat a thin film onto a circular copper sheet. Second, beans must be metallized by using Go to prevent interference with the electric field inside the counter. We can see the difference between before and after metallizing. And we can see after metallizing, the color is blue. And the TC97 source and different amounts of diluted Redox solution were prepared on gold-coated beans foil and then drying at room temperature. The Redox is to alter the detection efficiency of the system. And this is a picture. And for ample source preparation, after transferring the dilution. For ample source preparation, after transferring the diluted solution into an, it must be sealed and to prevent leakage and ensure safe handling. So, just like I say, ample is sealed to prevent leakage, and this is the movie to show how do we seal the input source by using the wire and 有点像是在手工的方式去拉那个皮，然后拉完之后大概是这样。And this is the LX source preparation for your reference. And the results. For 4 pi ES gamma measurement result, we can see the figure illustrates the efficiency extrapolation method used to determine the specific activity of TC99M using beam source. And we can see the absolute activity is here, and the uncertainty is about 0.5%. And for LSC counting, we take the average of the specific activity value obtained under different KP setting as the final result, and this is the uncertainty. And for R3 measurements, the ratio between CM method and the 4 pi gamma ion chamber is about 1.03. And for alpha measurement, the ample source is also calibrated using 4 pi gamma ion chamber, and this is the value. And the activity determined using the CM method was collected by normalizing the 4 pi gamma ion chamber result of the R3 ample source to that of R4. And this is the final result for CM method, and this is a specific activity. And the measurement result obtained from the 4 pi ES gamma method were compared and validated against the loose-derived CM method. We can see the ratio between 4 pi ES gamma and the CM method. The ratio between this method is 1.001, and we can see the difference demonstrates excellent agreement within the combined uncertainty range. And after that, we use the weighted mean specific activity calculation to determine the values here and transfer this data to calibrate the ion chamber and the dose calibrator. And we can get the calibration figure. So, for the ion chamber, the result demonstrates a high consistency with NPL, and this is the ratio for your reference. And next is for dose calibrator. This result indicates minimal variation between different geometry, 5 cc amper and 10 cc vial, and this is the difference. Both are within 2% compared to weighted mean. And this is the conclusion. We have successfully established a national transport standard for TC99M in Taiwan. This was achieved using a self-developed 4 pi ES gamma counting method. And we validated this method with CM method. And the result we can see show an excellent agreement confirming the robustness of 4πES gamma as a primary standard. And the standard is transferred to secondary measurement system for ion chamber and the dose calibrator. And it achieved, for ion chamber, it achieved calibration consistent with NPL. For dose calibrator, it shown the minimum measurement error within a acceptable limit. In the future work, we established a strong partnership with MMIJ in Japan to develop the 30 system, expanding our methodologies for fluorinating and other short half-life radionuclide. To further improve our efficiency, we are advancing automation and digitalization in our measurement system. This innovation will help reduce uncertainty and enhance operational efficiency, paving the way for more precise and reliable activity measurement. And this is the 30 for BIPM. For short life radionuclide, international transfer is impractical due to rapid radioactivity decay, such as fluorine-18 and TC99A. So in international, they developed a 30 system to estimate the short half-life radionuclide standard. And this is the reference, and it's my presentation. Thank you very much.
Did anyone have questions?
I have 3 questions, and the first one is because you have to do the magnetic dose calibrated. So will you do it before you calibrated it, and how can you calibrate this for our primary standard?
你的意思是说，在这个标准之前，我们怎么去做仪器的校正？Maybe I think before establishing primary standard, those calibrator used in nuclear medicine were commonly calibrated with serial reference source. Typically, they use Cobalt 57 and bearing 133 and Cesium 137. These 3 calibration sources span the energy typically encountered in nuclear medicine, ensuring that those calibrated accurate measurement activity. And for Cobalt 16, I think its energy about 122 keV, and it is just like TC99A. And the variant 133, its energy is just like iodine 137, and the Cesium 137, its energy is 62 keV, so it mimics just like 511 keV emission photon. So they use 3 calibration sources to calibrate those calibrators.
And the second one is because in your method, Cobalt X gamma method, and the efficiency is varied by adding different kind of loaders for these sources. So how about for CNLSC method?
Oh, here maybe we can see the description. In a CMS, the detection efficiency is adjusted by varying the quench level of scintillation cocktail, typically achieved by adding varying amounts of chemical quencher to reduce counting efficiency gradually。就是一般，就像我当初配这几瓶那个液态闪烁的样品的时候，我这每一瓶其实添加是相同活度的铯源。那正常情况之下，这样下去读，应该读出来结果应该是要一样。那我为了去改变那个量测仪器的效率，所以跟刚才在电子那边类似的想法，就是我在里面添加一些消光试剂，加在瓶子里面，那每一瓶加的量是不一样的。那这样子仪器所量消光试剂加进去之后，它会让这个仪器所量测到的读值，不管是能谱还是计数值，都会出现改变。所以这个时候我的计数值变了，那效率变了，那我就可以再去推算每一瓶的活度。所以刚才在这边其实因为刚才讲比较快，所以其实在这里的结果它就有秀出我添加不同消光试剂之后，我去做后续的活度评估，那评估出来的结果其实大家都还蛮一致的这样。
And the third one is besides PT99, and is there any radionuclides using nuclear medicine will be sent into NRSL?
Oh, maybe Indian 131 and gaining 67, and the Indian 123. Maybe.
Does anyone have questions?
Listen. Listen. OK， 好。那我用中文讲，就是这是我们在那个国际上，我们比如说，因为我们是国家实验室，我们的位阶大概在这里。好，那我们的角色就是在国内，我们是建立那个原级标准去实现物理量。那建立好这些原级标准跟物理量之后，我们可以提供国内各个二级实验室的校正。对，比如说像学校的清大娱乐中心，好，或者是像福协，好，这些都算属于二级实验室。好，那或者像其他像台电啊，或者是像科马公司等等，这些都是属于二级。那他们会把他们的社员送到我们实验室去做校正。那校正完之后呢，他就可以再往下去服务有这些社员或是仪器使用端需求的终端的客户，比如说是医院或者是在业界。对，所以我们的角色大概就是先把国际的标准先建好，然后让国内的不管是二级实验室或者是客户端，他们都有一个校正的依据。那我们校正的结果到底准不准确，我们就要参加国际比对。那因为我们台湾的那个应该是说因为政治因素的关系，所以其实我们没办法直接去参加最源头 BIPM 国际度量衡局的国际比对。那怎么办呢？我们就退而求其次去参加亚太地区有一个叫做 APMP， 这个是亚太计量组织，它大概会找日本、韩国，还有一些比如说泰国一些亚太的国家，然后我们就这些区域的国家一起去主办一些可能是社员比对啦，或者是有理想的比对。好，那因为我们不能参加 BIPM 比对，我们可以参加 APMP 比对。那比对完之后 ，APMP 有一些国家，比如说像日本跟韩国，它是可以参加 BIPM 比对的，所以我们就可以把我们跟 APMP 比对的结果间接连到 BIPM 上面去。对，所以这张图主要是秀，就是说整个校正追溯体系其实最高的是在 BIPM。对，那我们就是提供标准服务国内的各个实验室。
Anyone have questions?
Yeah.
I want to ask what's the different usage of these 3 types of source?
3 types.
Yes.
Why
The
I choose?
usage.
Oh, this one, this one, and this one is for primary standard. Just like I say, the main source is for 4πES gamma method, and this is our primary standard for TC99N. And the LS source is CN LSS method, and this method is这个 LSC 的方法算是我们去查核我们建的这个原级标准到底对不对，因为 CN 的方法是国际上在建原级标准的其中一种方式。那我们主要是把我们的技术发展起来之后，然后用国际上已经行之有年的方法去做一个比对验证。对，那 and the endpoint source is for 4πi chamber and dose per grade is， 就是我们把原级标准建完之后，刚才提到我会去评估一个加权之后的比活度结果。那我会用这个结果把这个标准传递到我们的二级件，那我们的二级件就是有离腔部分。那像这个4π伽马这张图，像4π伽马是这一台，那这台4π伽马的 ion channel 就是我们国家实验室维持这些液体色源的国家标准。那之所以会选这台 dose calibrator， 是因为在医院的核力科里面，这台 CRC 的机器是国内使用率比较高的一个，所以我们就把这个标准建完之后，先把标准传递到我们实验室的国家标准，然后再去跟这个台湾里面常见的这个活度计去做量测。那这台是在我们实验室里面，我们也有买一台跟在医院一样的设备在里面，然后去做校正这样子。
Anyone?
Page 17. What is the picometer and the function of it is?
这里刚刚有图，这是业余。And the picometer， 它其实有点像是帮助我们去做色源的滴定。那平常可能大家比较常见的是那个排配，就是那要怎么讲？反正就是色源的滴定器。但是色源滴定器在滴定的时候，其实它产生的误差其实是比较大的。那我们实验室的做法，这样真的超级像。我们实验室的做法呢，就是在滴定这些色源的时候，因为我们每次滴的色源的量其实很低，所以在重量的要求的精准度其实很高。那我们的做法就是会去用一个，就是它是一个它原本的形状应该是长这个样子，原本是长这样子，就是这个东西。这个拍控面的原本是长这样，然后当我们要去把色源填充在这里面的时候，我要去用火去做烧皮这动作，我要用火去让这一段融化之后，然后去把它给拉直之后，最后它就会变成这样尖头的构造。那我就会拿这个瓶子去把整个色源先抽起来，放到这里面去。那之后我再去做称重，之后再去做各个色源的滴定还有称重。那因为我们后续是要量比活度，所以我滴出去，我每次滴出去多少，我都要去做称重的动作。所以我只要有滴出去，我都要做一次称重，再滴出去再做称重。所以比如说我如果滴了30片，我可能就要量身几次这样子，对，这样我才可以确保那个我滴出去的量。跟我色源，跟我这个色源所接收到的量其实要一样的，所以我们的天平其实也是会买那种比较高精度的天平，可能会到小数点第4位或第5位这样子，去维持它的那个质量没有跑掉这样子。对。
Questions? Let's thank for his presentation.
I is going to talk about the MRI radiomics-based machine learning model for predictive BNCT treatment response in glioblastoma, and that's from
Good afternoon, professors and students. I'm the presenter Yan Han Chen, and today I want to share my research about MRI radiomics-based machine learning model for predicting BNCT treatment response in glioblastoma. Viral neutron capture therapy is currently available in only a few countries, and the patient arrangements of BNCT are still evolving and require further standardization. Therefore, the treatment response prediction for optimizing patient selection and treatment planning is crucial. And according to some studies, there is a correlation between MRI radiomics and treatment response of brain tumors. The treatments such as chemotherapy, such as radiation therapy or chemotherapy. However, no study has explored this approach, especially for BNCT. So our study aims to investigate the correlation of MRI radiomics and BNCT treatment response of brain tumors. So this study aims to develop a machine learning model to predict progressive disease in glioblastoma patients at 4 months after BNCT. The reason for choosing 4 months is because pseudo progression may occur during the first 3 months post BNCT, according to the clinical experience. And my preliminary results show the support vector machine model demonstrated the highest predictive performance with an accuracy of 90% and area under curve of 1 in validation process. However, despite all the excellent performance, further validation on larger cohort is necessary because our data is limited. Our data size is small to ensure the broad applicability. And this is my workflow of experiments. The left side is workflow, and I separated it into 8 parts. And right side is the corresponding methods and some results. First is data acquisition, including patient selection and MRI acquisition. First, patient selection criteria include patients with GBM diagnosis and with confirmed treatment response results based on renal criteria at 4 months after BNCT. The renal criteria is a commonly used criteria for evaluating the treatment response of brain tumor. And patients also have complete MRI acquisition, and the sequence includes T1 contrast and FLAIR imaging. And finally, 22 GBM patients were included, and they were classified into 2 groups, including progressive disease and non-progressive disease, according to their renal criteria results. And there are 15 patients belong to PD, and 7 patients belong to non-PD. And the MRI acquisition, we collect patients' MRI of 2 time points, including pre-BNCT MRI, which is the last follow-up MRI before BNCT, and the post-BNCT MRI, which is the first follow-up MRI after BNCT. And the reason for collecting MRI after BNCT is because in addition to predicting the BNCT treatment response, we also want to investigate the difference in MRI images before and after BNCT treatment, and how this difference correlated with treatment response after 4 months. And because this is a retrospective study, so the MRI scanners are different, including GE, Philips, Siemens. And this scanner difference could cause the variation of MRI image intensity. So we need image quality standardization. So next step is image processing, and purpose is to standardize the image quality. Our study used 4 steps to do this part. First step is bias field correction. You can see figure A. This method's purpose is to correct for intensity inhomogeneities caused by magnetic field variation. And second is we use resampling to standardize the resolution. And brain extraction is to remove the non-brain tissue in the image. And final process is disco normalization. And this process is important to normalize the intensity difference caused by different scanners. And you can see the figure D. This is the histogram of 3 patients before the normalization. And the green line represents 3 patients with different scanner, and you can see the difference of their intensities. And you can see after normalization, their intensity almost align together. And next is ROI segmentation. We use semi-automatic segmentation method. And this method is a providing function of a tool named ITK Snap. And semi-automatic segmentation allows us to just mark some labels on the image instead of fully segmenting it by ourselves. And this function saves time. It learns from the labels we provide and automatically complete the remaining segmentation task. And within this method, we segment 3 regions of interest, including tumor and necrosis region in T1 contrast image, and edema region in FLAG image. And right picture is my workflow. First, we use the T1 contrast to find the bright area. The bright area represents the tumor, and dark area is necrosis, and usually surrounded by the tumor area. And next, we use FLAIR to segment the edema region. And the final ROI are verified by the professional radiologists. And next is feature extraction. We use Pyradiomics to do feature extraction. Pyradiomics is an open source Python package for the radiomic feature extraction. And there are 3 main parameter settings, including label, image type, feature class, and we have 3 labels. And as for the image type, besides the original imaging, we also apply filters on the original image to generate another 2 images, including Laplacian of Gaussian filter and the Birkbeck filter. And we have 3 types of feature classes, and each class is composed of many features. And ultimately, this combination generates 3,051 radiomic features. Finally, 9,153 radiomic features were obtained from the regional features of each patient. Among them, 6,102 radiomic features were extracted from the regions in pre-BNCT and post-BNCT MRI scans. And other feature is called delta radiomic feature. And this feature were calculated by subtracting the feature value of pre-BNCT and post-BNCT radiomic feature. And it also generated 3,051 features. And next is feature preprocessing. We use, after extracting the features, we use the Weissenman-Whitney test to select the radiomic features that show significant difference between two independent groups, which is PD or non-PD. And this method analyzes the rank difference between two groups, and it's suitable for small data size. And the features with p-values smaller than 0.05 will be seen to be statistically significant. And our study select 456 features that shows statistical difference. And next step is feature selection. This study used two selection method to do this part, including MR method and ASO. Literally, MR is maximum relevance, minimum redundancy. Literally, this method selects features with maximum relevance and minimal redundancy with the prediction target. Relevance means the correlation between feature and prediction target, and redundancy means the average correlation of feature and other features. And this method uses MR score to quantify the feature importance by subtracting the redundancy with the relevance. And with this method, 19 features were selected. And if we look into distribution of 90 selected features, we find that around 46% were extracted from previous CT MRI, especially in tumor region. And the second method is this absolute shrinkage and selection operator method. This method is a regression analysis method used for regularization and feature selection to enhance the prediction accuracy of a statistical model. And regularization is to adjust the feature importance, which is absolute value of the feature coefficients. And this process also can implement feature selection by penalizing some coefficient to be exactly zero. And our study uses this method, selects 8 features among the 19 radiomic features. And this figure shows the coefficients of each feature. Notably, the 8 selected features show statistical significance with p-value smaller than 0.1 in Weissenman-Whitney test. The blue one is class non-PD and the green one is PD. So they are visually separated. And we also can demonstrate the visually difference in the color map. The left side is non-PD and the right side is PD. And next is to train the model. Before training the model, we apply synthetic minority oversampling technique to our data. The technique is used to address class imbalance in datasets by interpolating samples of the minority class. In our study, the minority class is non-PD, and we use the SMOTE to generate the synthetic samples to match the size of PD class. And after that, we can finally train the model. The dataset then be input to train 6 machine learning classifiers, and they have they each have different mathematical methods for classifying the data. As shown on the illustration right side, you can see same input data can be separated in different ways using different classifiers. And finally is model validation. Model validation is to evaluate the predictive performance of models. We use leaf-one-outpost validation and quantify the performance using performance metrics. The basics of leaf-one-outpost validation is almost the same with k-fold cross-validation. K-fold cross-validation is to split the data into k-folds. I will use bifold cross-validation to be the example. Each fold will take turn to be the test sample every iteration. And every iteration can have the performance results. And the average performance can represent the overall performance of this model. And so in our study, leaf-one-outpost validation also equal to 22-fold validation. And use the validation method just mentioned. Next, our study use 6 metrics to quantify the overall performance evaluation, including AUC value, accuracy, precision, sensitivity, specificity, and F1 score to validate the overall predictive performance. And this is the preliminary result. Results show that the ProVector machine model demonstrates optimal performance. But other models also achieve high performance with all metrics exceeding 85%. And the ROC curve also show the robust performance of the 6 models. And now I want to discuss the distribution of the 8 selected radiomic features. If we look into the distribution of the selected features, we can see 75% were extracted from pre-BNCT MRI, and 50% were extracted from tumor regions. So we can assume that pre-BNCT MRI, especially for tumor regions, may play an essential role in the task of predicting BNCT treatment response. And if we analyze it according to their feature type and image type, we can see 75% were extracted from image after wavelength filtering, and 62.5% were texture features. So texture feature after wavelength filtering may be the crucial predictor for predict BNCT treatment response. And according to Lasso coefficient results, the delta texture features in the necrosis region after wavelength filtering may be an important predictor for treatment response. And so you can assume from the results all models demonstrated robust performance with all performance metrics exceeding 85%, and it indicates a significant correlation between MRI radiomics and BNCT treatment response. However, due to our limited data size, further validation on larger cohort is necessary to ensure broad applicability. And my future work is to interpret the correlation between radiomics and the biological traits. And I will train the model only using preview to see the performance. And the conclusion is this study is pioneering study, and it represents the first investigation of MRI read-only features in predicting BNCT treatment response for GBM patients. And this is and the results indicate the MRI radiomics show promising potential in predicting BNCT treatment response for GBM. And this is my reference. Thank you for listening.
Is there any questions? I want to ask in page 31. I want to know what is the differences between the positive and negative coefficients.
Features with positive coefficients mean the feature has a positive correlation with the prediction target. Like you can see the first feature has negative coefficients, and you can see it means the feature have inverse correlation with the target, which is PD. So you can see in this feature, the value is lower in PD class. And that is the meaning of this coefficients.
Thanks. Why do all the models have the same specificity?
In my opinion, if the model has same specificity, it means they have almost the same true negative rates. And the reason for the same true negative rate, I think the reason is because I will show. It's the negative because the negative class data is I think because the negative class data is more concentrated because half of the data points were generated using interpolation. So their data point is relatively concentrated than PD class. And so I think it may be a reason that they have almost the same true negative rate.
Thank you.
The Laplacian of Gaussian filter is a technique used in image processing for edge detection. And its main function is to highlight the regions of rapid intensity change. And it can effectively detecting edges. And this filter also can help in reducing noise while preserving important detail in the image.
Can you explain what is price of the feature?
First order feature mainly describe the distribution of pixel intensities within an RI region of interest in an image. And unlike texture features, this feature don't consider the spatial arrangement of pixel, but only focus on the histogram of intensity values. And this kind of feature provides insight into characteristics like mean, very mean intensity or minimal intensity, such like that.
Page 25. I want to know what problem does class imbalance cause when training a model.
If we train a model with imbalanced classes, the model often focus too much on the larger group and ignore the smaller one. And even if the final accuracy seems good, but we can't make sure the model can recognize the minor class as well as major class. So fixing the class imbalance is important to get better overall performance.
Thank you.
Why did you choose this statistical technique to address the class imbalance?
Because I refer to many papers, and I found that papers with the class imbalance problem, they usually use this method. So I also choose this method to fix the problem.
Page 93. Can you explain what is this color map means?
I just want to use the color to demonstrate the difference of two class feature value. Because you can see left columns is non-PD class and right is PD, and we can visually separate it. We can visually see the difference in this color map, right? Can you see? Take the second feature, for example, you can see the non-PD is with have very lower feature value, and PD almost in this place. So we can visually separate it using the color map.
Page 21. Why did you choose these 8 features? Why did you choose these 8 features?
The 8 features is selected by Lasso. The number of features selected is not set by me. It is the 8 features is maybe I can tell why the number of features is 8, but maybe because other features, according to the Lasso training, they are not important. So also choose the A feature that is most important for the predicting task.
Page 12. And edema region is for flare. Can we use other methods to suppress water signals such as spatial saturation plus space?
Yes, but um, because we we can use some technique to suppress the water signal, but it's time consuming. So we just acquire the patient's flare because the signal is suppressed in this sequence. So we don't have to use any technique to suppress the signal.
And have any impact if we choose different methods to suppress water? Have any impact?
Is it have any
Impact.
impact?
Influence. Have any influence when we choose different methods to suppress water?
Maybe, in my opinion, different techniques to suppress the water can cause the image quality difference in my study. And the standardization of the image quality is important in my study. So I think it will have some impact on how the signal is suppressed.
Page 22. I want to ask what's the information you want to show on this chart?
I want to show the 8 features selected by Lasso. Is very has statistical difference in the 2 class. I just want to show, because you don't have building by this coefficient, and if we use this box plot, we can visually differentiate 2 plots using the box plot of the 8 features to let you to show the significance of these 8 features.
In your page 3, you said a word about pseudo progression. Would you please explain what is pseudo progression?
Pseudo progression is if a physician think the patient is progression disease after treatment by the MRI image, he will compare the MRI image before and after BNCT and to see the tumor change. To see the tumor change to identify the patient is progression. But the pseudo progression means in the first 3 months, the image after BNCT the tumor will seen as become bigger, but actually the tumor is not bigger because我用中文说，医生那时候在 BNCT 后的前3个月，他看到那个 MRI 影像，就是他会量测那个影像中就是有亮讯号的有没有变大这样，但是在这3个月之间的那个亮讯号并不是 tumor， 有时候并不是 tumor， 有时候是就是一些治疗后的发炎或是水肿，就是那个就不是 progression， 所以在这个期间就是虽然影像上判断好像是 tumor 变大，但事实上不是，所以要到3个月以后，就是那个发炎组织那些都没有，才可以就是正确的诊断。
So how do they diagnose the tumor response after 4 months? Another
image,
additional imaging, still MRI or CT? MRI, another MRI. So it may be scanned at 6 months?
4
at 4 months. But in your post-MRI scanning, you already can detect the edema and necrosis. So it might help to determine the true region of tumor. So maybe it already helpful to determine the tumor response to BNCT.
Maybe,
but they are not confident.
Yes.
May I ask page 20 and 21? You say you have 2 methods to select the future, and what's the difference between these 2 methods?
I think the MRMR method is more focused on the redundancy. They have considered redundancy as a selection theory, and LASSO is more focused on how important, how related the feature to the prediction targets.
And page 30. Maybe what is the ROC curve means?
The full name is recursive operator curve, and it can use a more comprehensive way to show the model performance. And usually the area under the ROC curve is AUC value, and more if the higher AUC value means the model performance is better.
And is there any question? No, and thank you.
今天3位同学报告 告其实都蛮不错的啦。那就是第一位同学的时间稍微短一点点哦。那但我另外发现一个问题，就是我们的moderator， 因为你们是负责就是要介绍，然后还要再掌控全场。那一般我们在研讨会上 moderator 还有另外一个很重要的角色，就是如果有 speaker 的时间或者是通常不是 speaker， 就是说如果在discussion 的这个 part 没有人问问题的话，这个 moderator 就必须要帮忙问问题。因为它其实就是有一个活络场子、活络气氛的一个角色所以呢，我会建议大家，就是当你在作为这个同学 moderator 之前呢，你要先去跟他讨论一下他今天的这个报告的内容。然后你自己就要先做好准备。假设呢有遇到一些冷场的状况那你要跳出来问问题。好不好？这是我赋予你们那个 moderator 新的一个任务。好，那这样的话，其实另外一方面也是提高你们问问题的一个次数，就是只要你当 moderator， 那你就可以那个有这些问问题的一个机会。所以就是我们尽量去让整个的流程是比较像是比较 formal 的这样子的一个conference 的一个状态。moderator 除了是介绍这个 speaker， 那甚至也可以做他的一些 interview， 那甚至也可以去做一个问题的一个提问。那这样子就是让整个的这个报告的这个内容还有衔接上是可以更流畅，这样好不好？所以如果你就是希望鼓励你们呢，就去接触你们要当 moderator 那个同学，你先跟他熟悉一下他报告的内容，然后事先先准备一些题目，这样子也没有关系。或者是你在当场你在台下听的时候，你就要去想一些题目。那其实这几次下来，大家都可以发现说，其实我们对于这个题目的发问其实是很简单的。我们甚至可以问说，为什么它的 data 要这么呈现嘛，对不对？那你怎么样去选择这一些数据来做这个 data？ 所以任何的题目的发想都是 OK 的，然后大家不要害羞，因为还是有一些同学的这个发问比较没有那么踊跃。那我们现在就是一个在校练习的一个机会，那就是鼓励大家不管任何的问题，反正你想干嘛就问，好不好？那这样子就是增加大家去参与的这样子的一个经验 ，OK？ 好，那就这样子咯，下次见。